Hi everyone, my name is Joshua and my partner Michael and I make up Team White Hat from the light side. So before we get into what we're doing, let's take a brief look at the problem. If I said smart store, what would be the first thing that pops into your head? AI, technology, machine learning? Well, smart stores incorporate all of these things. Smart stores like Amazon Go are essentially grocery stores that utilize technology at every point. So customers are able to put things into their baskets and just leave the store without having to wait at the cashier to pay for them. There's no human workers involved, so it's a new level of convenience where we don't have to wait in line to pay for our groceries anymore. And having no human workers, this also means that smart stores are able to operate 24/7, which is very, very convenient. So how does the dark side use machine learning to their advantage here? In 2019, Nassar et al. Showed how an adversarial patch placed on an image of a grocery item could fool a classifier into classifying the item as something else. In smart stores, it's often the case that customers would use their smartphones to take photos of the item that they buy as a way to pay for them via the store's app. And in this slide, we can see the first image shows an image of a lotion bottle with an orange as an adversarial patch on it. Now, what if I told you that the bottle costs $10, the lotion costs $10, but the classifier classifies it as an orange that's like 1/10 of the price? The customer happily walks away with the bottle of lotion, paying only the price of an orange. Now, Nassar et al. Considers this as a form of shoplifting, which in fact it is. So the team proposed a collab that aims to detect and prevent the adversarial patches from succeeding to fool classifiers. Their proposed algorithm has two components, the neural network and the explainable AI model. So in our attempt to improve the defense mechanism, we vary both the neural network as well as the XAI model used. So what have we done in the past few weeks? Firstly, we tried to detect the presence of the adversarial patch in these images using various XAI models. Now, the team originally used LIME, which is the Local Interpretable Model Agnostic Explanations model. And LIME is known to be accurate for most of the time, but we attempted to see how SHAPE, which is Shapely Additive Explanations, fared against LIME, whether it's better or not. So, this slide shows a LIME explanation, how it looks like. LIME will highlight the regions inside the image that were most important in determining the prediction. The idea is that the patch would be an important region if it was able to fool the classifier into classifying the item as something else. For shape, it also highlights the regions that are most important. A brighter red color here indicates that the region is more important. Now in this slide, we can see that the image has been classified as an American egret, mainly because of the part of the bird's neck that's curved, denoted by this very red region here. So, was our attempt successful? LIME was definitely a success, as it was able to detect the patch in the image. It was able to detect the patch inside the images with the adversarial patch. Shape, however, did not fare as well, as it actually failed to detect the patch. So now for a little code demo, I'll pass it to Michael to show a demo of the results of the various XAI models that we used.
Thank you, Joshua. We will now start with the demo. First, I will start with LIME. As we can see here, for this particular demo, we will be using the model ResNet50. In the beginning of the program, we will need to load the image first, which is here wine.png. And then we need to pre-process the image so that we can use it as an input to our model. And then here we ask for a prediction that is from our model here. And then we take the 5 highest confidence level prediction that is generated by our model. And as we can see here, ResNet has detected the image with 57% confident as red wine and 42% confident as wine bottle. And then we ask LIME for why such a prediction is outputted by our model. And then we first need to initialize our LIME explainer. After we initialize our LIME explainer, we inputted our image and our model prediction function to Lime, okay, where Lime process it and then come up with such an explanation. So here we can see which part of the image is detected by ResNet model that is affecting the result of our prediction. Okay, for a better reference, here this particular image is plotted here, okay, plotted in the original image, and we can see that ResNet has detected most of the wine bottle to produce such a prediction. And then we try the same method on our patch image, which is here winebanana.png. Okay, we use the same pre-processing method as well as asking prediction from our model. As we can see here, ResNet has predicted the image as 75% wine bottle and 70% red wine. And we ask Lime for another explanation on why such prediction occurred. Okay, and as we can see here, apparently ResNet still detects most of the wine bottle as the important part. Okay, and it almost completely ignores the patch. Okay, as we can see here as well, Lime has explained that this region is detected as the wine bottle, and this region is totally ignored. Okay, now moving on to Shop. Okay, so for Shop, we use the same model, which is ResNet 50, and then we use a dataset called ImageNet 50 from the Shop library. Okay, and then we created a function called fx, which is a function that wraps our model prediction function as well as the input preprocessing. Okay, and then for Shop, we need to initialize a masker. Okay, in this case, this is the inpaint Tilia from the Shop library. Okay, and then this masker will then be used to initialize the Shop explainer with the function and the masker as an input. Okay, and then we ask Shop and ResNet, both Shop and ResNet, to predict and explain on the prediction of these two images from the ImageNet dataset. As we can see here, this is the result that is generated by Shop and ResNet. The first image is a speedboat, and ResNet successfully detects it as a speedboat, and Shop explains it on which part of the image is detected as the speedboat, which part of the image affected the prediction of ResNet. And then on the second image, it is a hockey player and with a puck and stuff, and here ResNet successfully detected as well, and Shop explained it with such an explanation. Now we try this method again with our patch image, where previously ResNet and Lime successfully detected as still a wine bottle. In this case, okay, we use the same image winebanana.png as well as same preprocessing method. Okay, we preprocess the input, and then we show the image here. This is exactly the same image as we used before. And then we use the same function that we have created before for our dataset. Okay, and then we input the masker as well as the function. But now we ask for an explanation and a prediction for our patch image. As we can see here, the result, Shop performs poorly considered comparison to what Lime and ResNet has detect as a wine bottle, but Shop and ResNet detects it as a church or a mailbag, honeycomb grill, none of which are wine bottle. Okay, so apparently Shop and ResNet combined together fails to predict the patch image correctly. Okay, now let's continue with the explanation to Josh.
So those are our attempts to detect the patch. We saw that Lime worked relatively well, but Shape not so much. Now, detecting a patch is great, but we can also look at preventing the patch from fooling the classifier. Instead of only detecting, we also tried to go one step further and find a classifier that's robust enough, in a sense that it's able to classify an image correctly even with the presence of the adversarial patch on the image. And the motivation behind this is simple. Detecting the patch may allow the smart store to prevent the customer from buying the item, since there's a patch on it and would likely require the customer to take another photo of the item. Preventing the patch from doing its job, from fooling the classifier, allows the smart store to still sell the item to the customer at the correct price. So the neural networks that we work with are pre-trained models, mainly VGG16, VGG19, and ResNet. So in this slide, we have a summary of the top 1 and top 5 accuracies of the models that we're using. The top 1 accuracy indicates the probability of the prediction, with the highest probability being the correct target label. The top 5 accuracy is the same, but instead of only checking the prediction with the highest probability, we check the ones with the 5 highest probabilities. And here we can actually see that VGG16 and VGG19 have similar accuracies, while ResNet is slightly better than both of them in both cases. So from what we found, VGG19 is slightly more robust in the sense that it was able to detect the wine bottle in the image below, which contains an adversarial patch in the form of a banana. As you can see here, the labeled wine bottle has a confidence rate of 19%. Now, this is still a low rate, so even though VGG19 did not classify the image as a banana, it also did not confidently classify the image as a wine bottle. However, it should be noted that it does better than VGG16, which classified the image as a banana with a relatively high confidence. Now, ResNet, on the other hand, actually worked better. Even with the adversarial patch, it was 75% confident that the image is of a wine bottle. Now, why do we say this works better? Well, generally, a confidence of 75% is preferred to a confidence of 19%. There's a higher chance that the prediction with a 75% confidence is more likely to be correct. And now again, I'll hand it over to Michael so he can show you how we got these results.
Okay, thank you, Joshua. Now we will take a look at the code for VGG16, VGG19, and ResNet. So VGG16, this is basically the code that is made by the research team that made the research paper that we used. Okay, where there's a transform image function where this image is supposed to pre-process the image so that it can be used for the VGG model. Okay, and then here we generate the prediction for the images that we will use, that will be inputted as the input of our VGG16 model. Okay, here for the image, we also print out the top 5 predictions that is predicted by the VGG model. As we can see here, it detects the picture as 52% wine bottle and 43% red wine. Now, the explanation that we got from Lime is the same as what we have done previously in the Lime versus Shop demo. This is the exact same code, and as we can see here, it detects this part of the wine bottle as the important thing that makes it predicted as a wine bottle. Okay, here's the more clear image, and then we do the same experiment on the patch image. Okay, and as we can see here, it detects the image as a banana. Okay, it detects the image as a banana, and we ask Lime on why this kind of prediction occur. Okay, apparently ResNet failed to see the important feature of this particular image. Okay, and as we can see here, it detects the hands and it detects this part of the image, which is none of it is in the wine bottle. Now, to improve this, we tried to implement VGG19, which is a newer version and a better version from VGG16. Okay, to do so, because they are basically on the same library, we use the exact same code, but we need to change this from VGG16 to VGG19. Basically, that's it. Okay, and everything is about the same. Okay, and as we can see here, it detects the same thing, almost the same thing, for the plain image, 51% red wine and 46% wine bottle. As we can see, Okay, for the plain image, the explanation is about the same as well, on which part of the image is the important part that affects the prediction. Now let's try with the patch image. As we can see here, apparently VGG19 is more robust than VGG16, where it detects it as a wine bottle, although the confidence level is quite low, it's 19%, and also banana is still here of 0.08% confidence, which is very low. But indeed, this confidence level is also not so good. Okay, on the explanation for this image is, as we can see here, VGG19 detected better. Okay, so it still detects part of the image as a wine bottle. Okay, this part of the image, which is the wine bottle. Okay, this part. Now, to further improve the robustness of our predictor, we try implement ResNet. Okay, this code is what we have seen before in the ResNet versus Shop. Okay, this is the same code, and as we have previously seen, it detects it as 57% red wine and 42% wine bottle. And yeah, this is basically more robust, and given the patch image, it even detects the wine bottle with 75% confidence, which is much better than both VGG16 and VGG90. Now, that's about it for the three code of the model. Let's continue to Josh.
So far, we've varied the XCI model as well as the neural network. But let's try and see if there's anything else we can do. And there actually was one thing that we haven't touched yet, which is image preprocessing. We can preprocess the image before feeding it into our neural network. And this is exactly what we did using the neural representation purification technique called the NRP technique. So now, the image on the bottom left shows the perturbed adversarial image. After purification using a trained purifier, the image on the left becomes the image on the right. And in other words, this technique is meant to remove the random noise that should not have been present inside the image. And this is done by minimizing the feature difference between a clean and perturbed image. So let's see whether this purification helped. Preprocessing the same image of the wine bottle with the banana adversarial patch, we see that ResNet is able to classify it as a wine bottle with a greater confidence of around 91% compared to the original 75% when the image was not purified. Again, I'll hand it over to Michael to show you how this purification was done and how we got our results.
Thank you, Josh. We will now take a look at the purification technique called Neural Representation Purification Technique, or in short NRP. And this purification technique is proposed by Muzammal Nasir. Okay, and we will be using his script called purify.py, where it will purify images that is stored in adv_images folder by using the purifier network NRP-ResG, which is also based on the ResNet model. We will be generating an image called winebananaclean.png that we will use as an input for our prediction model. We pre-processed it first as well. This is the same code as what we have done before, only this time the image has been purified by the NRP technique, and we ask for a prediction, and as we can see here, our ResNet model is now 91% confident that it is a wine bottle. Okay, this is significantly better than what we got before. Okay, what we got before is 75% confident that it is a wine bottle. This is with the plain patch image and ResNet predicted as 75% confident level of as it is a wine bottle. Now with the purified image, it is more confident, significantly more confident, with 91% confident level that it is a wine bottle. And then we ask why such prediction is given by our ResNet model. And as we can see here, as explained by Lime, that ResNet model almost ignore completely the patch image. Okay, here's the area of the patch image. Okay, we can see clearer here that ResNet detect this part of the image, which is the wine bottle, and then this part, which is the patch image, ResNet completely ignores it, and Lime can explain it successfully. Okay, so given the purified images using the purifier technique, can significantly improve our ResNet model robustness. Okay, now back to Josh.
Okay, so now we're up to date on what we've been doing for our own collab. Now let's take a look at how we've progressed on the challenge that we took up. So the challenge that we took up is actually the one posed by Dark Han Solo, which is to detect the 1 pixel attack. So just a brief introduction to the 1 pixel attack in case you're not familiar with it. Now in these images, you can see that there's 1 pixel circled in red, and that's the perturbed pixel. This one small perturbed pixel actually caused the classifier to misclassify the image. So here, instead of a cup, it's classified as a soup bowl, and instead of a bassinet, it's classified as a paper towel. So how have we tried to defend against such an attack? So we first examined whether a one-size-fits-all approach works. We tried to we tried to use an XCI model to detect this perturbed pixel, as well as robust neural networks to prevent the 1 pixel from fooling the classifier. And note that the images here that we're using have also been purified using the NRP technique. So basically, we're using the same technique as we did for an adversarial patch on this perturbed 1 pixel. We used both ResNet as well as Lime, as both of these were actually the best models among the ones that we examined when we were doing the adversarial patch defense. So how did this work out for us? Well, initially, using ResNet alone, this pixelated image of a ship was classified as a truck. However, after purification, ResNet categorizes it as a fireboat, and this is not as desired, but it's definitely a step in the right direction. So the classifier was able to identify that this image contains a water-based vehicle rather than a land-based one. So definitely it's a step in the right direction, even though the classification is still wrong. Now on the far right here, we see the outcome of the image after using Lime, which features were most important in the explanation. And we can see that the 1 pixel that perturbed the image, which is this black dot here at the top right corner circled in red, is actually highlighted by Lime in the far right picture. So definitely Lime was able to detect that this pixel was an important feature. So in other words, it was able to detect the perturbed pixel. So however, ResNet failed to classify the image correctly, and Lime explained this very well. It highlighted that 1 pixel, indicating that it was an important feature in the classification, and that's likely why ResNet classified it wrongly. So again, let's see this in action.
Okay, for the 1 pixel attack, we will be using the same defense mechanism as what we have used for the adversarial patch. As we can see here, we will be using an image called ship.png, which is an image of a ship that has been perturbed by the 1 pixel attack. We will be using the same purifier network, which is the NRP technique, by using the same script purify.py as well as the same purifier network nrp-resg that is based on ResNet. The output of this purifying technique will be called shipcleaned.png that indicates it has gone through the purifying technique, and this image will be pre-processed the same way as what we have did before and be used as an input to our ResNet model. And as we can see here, our ResNet model has predicted as a fireboat. Although it does not predict it as exactly ship, but it has already detected as a fireboat, which is the same category of vehicle, a water-based vehicle. And when we ask Lime on why such a prediction occurred, as we can see here, Lime has generated some explanation that ResNet took most of the part of the ship, okay, to classify it as a fireboat. But as we can see here, there is one small part here that is not on the part of the ship. And when we took a closer look, apparently that small part that is not in the ship is the 1 pixel attack. So although ResNet failed to classify it accurately as a ship, instead it predicted as a fireboat, Lime can still explain and detect that, oh, there's a 1 pixel attack that is placed there, that is placed there by the 1 pixel attack. Okay, there's a 1 pixel that is a perturbation to the image. I guess that's all. Now we can continue with the explanation.
So what have we discussed? In our own collab, we varied both the XCI and the neural network model. We also introduced image purification as a pre-processing step, and we saw good results against the image with adversarial patches. In terms of the 1 pixel attack, we employed the same technique, and we saw that our techniques were able to detect the 1 pixel that was causing the image to be misclassified using Lime. However, we also saw that the neural network was unable to prevent this misclassification from happening. ResNet was not robust enough to look past that 1 pixel and classify the image correctly. However, again, we did see that classifications made on purified images using the NRP technique were a step in the right direction, and we definitely hope to improve this in the future and see whether it is possible to detect and prevent the 1 pixel attack. So that's all from us, and thank you for your attention.